So yes, here we go again. I hope you like exponents. We're hitting it, I think this is probably for the third time. This will be a little easier than the fraction exponents, but here we go. So when you're dealing with Euler's number, which I will now just call e, you can also do exponents. So in this first example, e to the 9th times e to the 6th, we know we add those exponents, which would give me e to the 15th. Over here, on this example right here, we know that numbers are numbers, so 60 divided by 12 would be 5. When I'm dividing with exponents, I subtract, so I will get e to the 5th. This third example, don't forget that the 10 actually has a 1, so this would go to the 10, so it's negative 10 cubed, and then I would also multiply the negative 3 here, giving me e to the negative 15x. Okay, so two problems. One, negative 10 cubed is negative 1,000. E to the negative 15th. Don't forget that e is a number, and I cannot have a negative exponent. So that e to the negative 15x will come down to the denominator and become positive 15x. And now let's just look at the calculator. If you look on your calculator right here above the ln button, you have e to the x. So you're just going to type in your calculator e. It'll automatically go up to the exponent. You type in the 6, and e to the 6th is 403.429. And over here, we're going to type it, do that same button, get to the negative 0.28, and e to the, it's going to be 0.756. Now let's look at two application problems using e. Annual sales of a product can be modeled by the function capital S equals 6,000 e to the negative 0.15 t, where S is the number of units sold and t is the years since the product went on market. So I want to create a graph. It says graph the model, where S is the units sold, and t, which is going to be my x, is the years. And if I look at the equation, I know, first of all, that the 60,000 is going to be my y-intercept, so I think I'll count by tens. This would be 60,000. This is 10,000. So sales is going to begin at 60,000. So this is on the calculator portion, obviously, so we're going to put this in y equals. So this equation right here is going to go into y equals. And I see that after 2 years, I have about 44,000. So 10, 20, 30, 44, which would be about here. After 4 years, there's about 33, which is about right here. After 6 years, there's about 24. It's about right here. And after 8 years, we'll just go ahead and add on 2 tick marks here. After 8 years, there's about 15. Since I have no horizontal shift, this is going to be a decay that looks like this. Like I said, at 6, this was 394.18, and actually I'm not going to put dollars because I'm trying to find units, and I don't know if it's units of dollars, units of barrels, units of what, so I actually don't know a unit, so I'm just going to put units. To me, this is the most eye-opening application for E. You spend $1,000 on a credit card that has 16% APR compounded continuously. Continuously means there's never a break. It's not monthly, it's not daily, it's not quarterly, it's continuously. Typical credit card. If you pay nothing, not counting late fees, what will you owe after 1 year or 2 years? we now will introduce the compound continuously. So the key here is this word continuously. The compound continuously equation, again, please make sure you put this to memory, is A equals capital P e to the RT. We call it the PERT. This is compounding continuously. If you don't see the word continuously, then you don't use PERT. So we have a principal of 1,000 e to the rate 16. Sorry. And the time is after 1 year. Typing this in my calculator, I find out that after 1 year, I will owe $1,173.51. So, for nothing. I have $173 after a year of interest. Now let's look at what would be at 2 years. So, same principal, same rate, but 2 years. And I'm going to owe $1,377.13. It is crazy, but the credit card companies want more.